So I've been developing a project on knowledge representation with a colleague from La Coruña, Pedro Caballar, on the representation of knot and string puzzles, where you have the interaction between strings, flexible objects, holes, and rigid objects. And one of the questions that we're trying to solve, and that's the reason why we got interested into that, is that whenever I try to untangle the puzzle, I usually make it more complex and make a worse entanglement if I don't have a model of the object. So somehow I'm creating a representation in my mind, but the representations that we got, the mathematical representations that we use to computationally solve these puzzles, are far away from the way we handle the puzzle. So I wonder if you have any comments about it.
Well, yes, I think some of the problems with all the mathematical representations of knots, that they describe a kind of a simplified world in which some idealizations are made. For instance, they always talk about loops, closed loops, and very little attention is paid to the question of the physics and the geometry, not the topology of the knot. So I do think that in the actual practice of knotting, in the actual practice of creating a knot or disentangling it, we do pay a lot of attention to those elements. We have a kind of an implicit knowledge that comes from the fact that we learn to tie knots and learn to untie them. And this knowledge is relatively hard to unpack because we have to be able to find the key ingredients of the knotting abilities. And these key ingredients are not just shapes, they're not just properties of the object, but they are shapes in action. That is, shapes that are constructed by some gestures that we make, which transmit energy to the piece of rope, and this energy is used by the piece of rope for storing a certain shape. And what I would like to demonstrate is some of these basic elements of the knotting ability by going to very simple operations that seem to be important and essential to everyone who's able to tie a knot.
So then it seems that what you're saying goes a bit against our common sense of solving mathematical problems, a common way of solving mathematical or physical problems. Because whenever I get a problem on physics, the first thing I do is I draw a diagram. And it seems that we reason better with diagrams rather than with the real thing. But when you draw a not draw diagram, I agree that there is this oversimplification. But how can we solve a mathematical problem without this kind of abstraction?
Well, now diagrams have an interesting challenge because they want to represent not only the shape that we have to produce, that is the final knot, but also the different steps to get to that shape. And so they introduce a number of conventions like directions, like sequences, for instance. So much so that typically the best way today to learn how to tie a knot is to go to a tutorial on YouTube. And the best tutorials actually are those that are taken from a viewpoint of the knotter. So when I will demonstrate later on some of the basic properties of a knot, I will take advantage of this facilitation, which is provided by taking the viewpoint of a knotter, which has to be assumed by the person who's going to tie a knot. But I don't think that we are so far from a mathematical analysis. Simply, we are a bit behind in terms of the key ingredients. So in a mathematical analysis, you have to look for a decomposition of a problem into smaller items, and then hope that the items that you individuate are such that you can recombine them syntactically to produce a representation of the object which you are trying to analyze. And so my challenge here is to provide an analysis in terms of atoms for the knotting capability, and these atoms are not the ones that one typically expect. So I want to show that some of those key ingredients are a certain understanding of basic forces and the way in which these basic forces are stored in the geometry of the shape that the knotter is manipulating.
How much of these basic forces are common sense and how much are actually learned at school?
Well, I think it's mostly implicit knowledge. So it is not something that you can easily propositionally unpack, and this is why the project is interesting. So it's we have to the mental representation of a knotting process is not just having an initial shape, some intermediate sequences, and a final shape, but it's a dynamic representation of the way your body interacts with a piece of rope, and the way in which this representation is updated along the construction of the knot. Because in this process, some of the forces are deployed but then no longer used, and some other forces are used. The geometry changes, and the geometry changes also the disposition of the forces, and our understanding of how these forces are deployed. So I do think there is a common sense idea here, but it is not articulated propositionally. So the difficulty is actually to find out exactly what it is by trying some of the basic knots and see what is really important in them.
Maybe we could dissect a knot now and
well,
see at every point what we're talking about.
Yes, it would be nice to have along with a movie that represent the activity of knotting, some kind of sensors in the rope that tell you exactly how the forces are distributed in the rope. So that could be a next step in modeling the knotting activity.
From the technical, in terms of knowledge representation point of view, what's missing in our solution is really including some sort of the idea of tensions and forces and blockages. What we currently we're not working on the mathematical knots, we're dealing with physical knots, so we have to change some of the representations to include physical rigid objects as long as strings and loops. But we still don't have the notion of contact and what it means to have a contact, what it means to feel a contact. Maybe and the next step would be to include in our diagrams this notion, this kind of a naive physics notion about contact and tension and blockages.
I agree, it's an important point, and another thread that comes out of this discussion is that we also have to consider very closely how large is our notion of a knot, if it does or does not include the object which is used for creating the knot. So if you tie a knot on a bar, for instance, is the bar part of the knot or not? And I think there are reasons to say that the external object is actually part of the knot, once it is, because the properties of the knot would not be stable if the object was not there. What I demonstrated, of course, is based on my own practice as a sailor, and a person who reads knots manuals. But of course there are many things to be explored here. For instance, we need better ethnographic records. We should probably interview other people, other knotters from different cultures. Although I suspect that the very same knots are used in all cultures because of the mathematics behind. No, there is not much cultural variation here. But still, it would be interesting to create a set of questions to knotters to elicit the basic operations, so to make sure that this representation of the basic operations in knots are actually universally used.
So I want to ask you a puzzling question. So is this a loop? I can't make it. If you look at this side, it is. If you look at this,
of course.
It's not at all. But we can use it to pass an object through.
Yeah, of course. So one point that I want to discuss as well is that there is a notion of perspectivality in knotting. I mentioned it when I said that it's important to have the viewpoint of the knotter when you try to explain what a knot is. Maybe many people don't understand what a knot is because I try to teach you. You're in front of me and I should put myself
Right.
in a perspective which is shared. And it's not just shapes in action, it's perspectival shapes in action. And this is important. You see when a loop has a certain perspectivality, so it depends on the tension that you put on the rope, and it creates a certain shape which is actually the same from you and me. So this is it is a counterclockwise loop, and it is the same for both sides. But still, there are many other ways in which you can look at a knot, and the perspective is important for getting the internal representation of how the forces are deployed into the construction of the knot.
You made a good point about the perspective of making a knot, but there is also a problem of the definition of things that we should define on the vocabulary. So, for instance, would you call it a hole? Is it a hole on the string? It's certainly a hole because I can pass through things, and I can only pass through things if it's a hole. But I wouldn't call it's a hole on the string. It's a hole in the air.
No, I think we need some kind of functional definition of a hole here. So it's a kind of a transitory hole, but it's only functional. It's not a hole in the classical sense, because it doesn't satisfy any of the physical and geometrical properties of a hole. But it does satisfy some of the functional properties of a hole, so it works like a hole. I would say that loops can behave functionally as if they had a hole in them. So maybe we represent them as hole. The standard way to teach a ball line is to talk about the hole. The first loop that you create when you create a ball line is the hole that the rabbit visits when he actually is the hole the rabbit exits from before taking a ride around the tree and getting back to the original hole. So this whole representation is part of the folklore about knots, and I would like to respect it, but I don't think it is a hole in the proper sense.
But that's the way people teach knots. They call it a loop as a hole.
Yeah.
So they solve problems reasoning about holes rather than reasoning about string.
Yes.
So it's kind of a reification. So they reify an object.
Or fractionalize it.
Fractionalize.
Fractionalize.
I'm going to demonstrate some simple knots with an eye to the logic which is used in knot building, and an analysis of the different parts of knots, which are events occurring in space-time, by using a piece of rope which has certain physical properties which I'm going to talk about. So let's start from the rope. There are many ropes, but for our purposes we can model a rope simply as a set of small cylinders. So you have small cylinders, one next to the other. And ropes have physical properties. One of those is that because of this particular physical geometrical structure, certain actions that you perform on the rope, like a torsion, have consequences on the shape of the rope. So if you make a torsion clockwise, and it is clockwise in the two senses, no matter how you look at it, it's going to be a clockwise torsion. This produces a coil in the rope, which is technically called a bite. Produces a bite, and this bite has a shape and a certain direction. So if I make a clockwise torsion like this, immediately we produce a counterclockwise series of loops. So this, what happens here is that some energy is stored in this configuration, some energy which you can use to stabilize the knot. And this is the basic idea behind knotting. So you create a torsion, or you can create a bite, but at the same time you produce a torsion, because as you see the torsion is not going away simply. You store some energy in this shape, and then you can use this energy to stabilize the knot. There is something that you don't want to do, so this is not going to take advantage of the stabilization. But you want to do things like that, so that this energy, which is stored in this part of the rope, is preventing the rope to slide when you have a blocking part. So, and this is the basic function of all knotting processes. So there is something physical about that, which is not only topological. It is a mixture of topological, geometrical, and physical properties. So I repeat. Anytime you have a bite, you have some energy which is stored in the rope, and this energy could be used to stabilize the knot at some point. And typically the stabilization you do by either using another part of the rope or using an external object. So for instance, if I have an object like that, I can create a typical knot like that. And some of this is tight on the object because the object itself is preventing the knot from unfolding, so to release the energy which has. And at the same time, this energy is keeping the knot in place. Terminology, when we discuss knot construction, we talk about the standing end, which is the part of the rope you're not working on directly, and the working end, which is the part of the rope you're working on directly. So when you do a knot, you can operate in different positions of the rope, but typically you work at the working end because you have a free end that you can put into different shapes. This is not what happens in general. So it's not the general case. The knot manuals will talk always about manipulating the working end, but actually you can do a lot of things inside without even talking about the ends. You can create knots, actually, and knots topologically, but they are going to be very stable knots by working inside the piece of rope. So this is a very respectable knot, and it is created without any manipulation of the working end. So the distinction does not apply in all cases. This very same knot, and this is a point we are going to go back to, can be created by manipulating the working end. So it's exactly the same knot that you will do, and I repeat it sorry. I repeat this one, but we'll edit it out. So this very same knot you can do by manipulating the working end. It's exactly the same knot as before, but it has not been created by the superposition of the two loops. It has been created by making some operation on the working end. One thing that has to be discussed, I think, at some point is knot equivalence. How do we understand that two knots are the same knot? And there are many knots which are equivalent, and people simply don't know, because the way historically they're produced or they're taught is so different that it looks as if they're different knots, but actually they are all the same knot. And in this particular case, both of the knots that I demonstrated, so the first knot, which is created by a superposition of two loops, and then the integration into an object, or directly by manipulation of the working end. This knot here are taught in very different contexts and situations, and they are, but actually the result is the same. Just demonstrate the equivalence of two knots. They are both clove hitches, produced by two completely different means, and actually an important thing is that these are not knots topologically. These are two instances of an unknot. Only when the object, if you only look at a piece of rope, there is no difference from any of those and a straight piece of rope topologically. They're just this. And this you can clearly deform into a straight piece of wood. So the two ways to produce it, a cloth hitch, are those. You create two loops, and then you superpose them in a counterintuitive way. So not not in such a way as to create a continuous spiral. You create the two loops by two similar torsions, a clockwise torsion, and then you superpose them in a counterintuitive way, and then you fix them in on a pole, for instance, and you get this knot, which is extremely useful because it's very stable and is very easy to untie. But you can do exactly the same knot by a completely different process. So using this time the running end and tying the knot in this way. So you just go on over the other side, come back, and find this place which is between. And you will see that this knot is exactly the same as the knot which has been created, and we'll make a demonstration that it is exactly the same, which is as follows. 1 and 2. And subsequently 1 and 2. And as you can see, the two shapes are exactly the same in the two cases. And both are instances of an unknot, and this is why they're very useful, because not being real knots, they're very easy to untie. The cloth hitch that I just demonstrated is a wonderful knot, because, well, it's very easy to construct. It's very easy to construct, and the construction, I will do it another time here, is like that. And it will be very helpful if you want to tie an object temporarily on an existing pole or even on another piece of rope. And the pragmatics of knot is very important. It's important to know why you are knotting, for what purpose you're using a certain knot. So if it is for a temporary use, you want the knot to be both stable but easy to untie. And there are very degrees here. It could be, of course, the more a knot is stable, the more difficult it is to untie. There is a trade-off to be found. So if you want to tie your dog to a pole, this is a great knot because it will stay for the time you go to the grocery shop. Typically, dog owners do this kind of horrible knot, which should be forbidden. And as you tie it, it's going to become so stable that it will be, especially as the dog is going to pull on the rope, it will be very difficult to untie. And the same holds for boats, for many other cases in which you need this kind of stable but temporary situation. One thing that surprises most people who come to the knot world is that actually very few knots are really indispensable. So statistics of usage in sailors' world tell that maybe 6 or 7 knots are really used all the time, and all other knots are just decorations or intellectual games with knotting. So there are really few knots which are used, and because they're proven, they're easy to make, easy to untie, and you don't need any other knots once you are both. So I mentioned the cloth hitch as a very stable knot, but easy to untie, that you can create on a pole by a simple chain of operations. The object that stabilizes the knot, which is in this case the object you're using to tie the knot on, could be an independent object, but it could be also a piece of the rope itself. And this is what happens in many cases. So for instance, in order to have a very stable knot on a pole, you can use a pole, and then instead of creating the cloth hitch here, you create it on directly on the, let me do it this way so it is more stable, on the rope. So you use the rope here as a stabilizer, and then you do your small knot here. So this is common practice, and you have a knot which is tied on the same piece of rope, which is on the very same piece of rope. It's a kind of a self-reflexive knot. Most of the energy is taken by this part of the knot here, very little by this part of the knot. So when you pull, very little stress is put on the knot here, and it's much easier to untie later. So the typical trick is to let the rope do most of the work and let the knot just consolidate a situation. This is an important part of the pragmatics of knots. I will demonstrate another very important and very used knot, one of the most used knots in sailing, which is the bowline. There are many ways to do a bowline, but the most known way is to create a loop which you hold in your hand for a little while, and you hold this loop. Typically the bowline is used for fixing an object to another object, so let's use the other object here, but it is not essential. You can create a bowline independently. And then the running end is doing a certain path to close the knot. So it has to enter this loop, make a small journey around the working end, and exit the loop in the same direction in which it has, in the opposite direction as the one it has entered it. So this is a bowline, used for tying an object to another object, and it's very easy to untie. So I will say something more about the bowline because it is an important knot, and I will enter into the mechanism of its construction. So as I mentioned at the beginning, when you create a knot, you take advantage of the fact that a torsion stores some energy into the loop, and this energy is acting in a certain way. It tries to be released, so you can use this energy for stabilizing the knot, and so this dictates also a certain necessary sequence for generating the bowline. When you get back from the object you want to tie the bowline to the loop, there is only one way you can enter the loop. If you enter the loop from here, for instance, it's simply not keeping the running end is simply not keeping the loop stable. So you just know and you feel it that the only way to enter the loop is from this direction. And then logic dictates that you have to exit the loop from the same direction, actually from the opposite direction from which you entered it. And so the sequence is at this point completely predetermined. So the bowline is interesting because it's hard to teach. Typically, people spend a lot of time doing the first bowline. And there are some symmetries in it, so I started it from this, by using, from my point of view, the working end on the top of a standing end. So I used the working end of the top of a standing end, and then at this point a certain sequence was predetermined because of necessary because of the forces which are contained in this in the loop. Again, the bowline sequence. So there is a symmetry in all knots, and you can. It depends on the way you start the knot. So I started the first knot with the working end at the top of the standing end, but it could have been the other way around. So it could have been that the standing end is on the top of the working end, and again here the sequence is predetermined. So there is no you have to do things that block the loop, and so you have to follow a certain set of movements, that take you to the construction of a bowline. I hope I'm doing it properly here. Not completely, yes. Okay. So let's say you have two independent pieces of rope, and you want to tie them together. There are many ways to do it. This is also something important because at some point in life, one of your ropes is not going to be enough. Your line is not enough, and so you want to join it with another. You create a bight like this one, and then you insert a loop in the bight by just running it all around like this. And this, I think, actually, this is the correct one. Okay. So you have two pieces of rope here, which are connected by this very common and taught as such connecting knot. But look what happens. If it turns out that the two ends are actually ends of the same rope, by doing this particular set of operations, so you create a bight on one end and a loop on the other end, and the loop crosses over and is stabilized onto itself, so that it is a loop. Well, you end up with a bowline. So this is exactly a bowline as we showed before. So again, nobody knows. In the sense that nobody tells you that the two processes, which are typically done on independent objects, boil down to the same knot when there are not two independent objects, but there are two parts of the same object. So there is an interaction here between mereology and knotting, which has to be explored. So you can run the reasoning in reverse, which I do it for the first time because I never did it. So if you create a bowline in the way which we discussed earlier, if you create a bowline, and then you cut here, you get two pieces of rope which are very well connected by the knot which is typically used for connecting them. The cleat hitch is another example of a knot which only exists because only can work because it takes advantage of some configuration external to the line. So it is typically done this way with a final loop which is so made that the energy in the loop is blocked by this part of the cleat. And it's a very stable knot which is used commonly for mooring. There are different configurations of a cleat. This is one possibility. There is another one with a T, but the two elements of the T work exactly as the two points here. So there are reasons to have the T as opposed to that. The T is used for small ropes, not like this one. The two poles are used for very large ropes, but the principle is the same. And once you're done, so it's never running in this way, but once you're done, you can simply take it away, and it is completely free. So topologically, there is no knot here. I want to demonstrate a couple of knots which are maybe less used but still interesting. They're interesting because the way you produce them is typically is not the way you find it on websites or so real life is different from websites. Websites somehow take some of the diagrams for knots, which usually have this kind of thing going around and doing a number of things. And make an animation out of this. But actually, in most cases, this is completely awkward and impossible to do because every time you do this, you create this kind of torsion that's going to tangle your knot. So this is an interesting knot which is called the ship shank. The ship shank is used for reducing the size of a rope. which might be interesting in some cases, or for isolating a part of a rope which is maybe not in good conditions, and it is then secluded in a portion of a knot and is not holding the weight of them anymore. So the ship shank is produced like that. You create a small loop, a large loop, and yet another small loop. And then, as you remember, these loops contain some energy. So the two loops at the end of it are the two things which are going to provide the energy, and the internal loop is not working as a loop, but only as a stabilizer over two small loops. In order for it to be a stabilizer, it only can enter the right loop from this side, and it only can enter the left loop from this side. You can make, and as you can see, it's an incredibly stable knot. So if one of these portions is not ruined or broken, you can still have or almost broken, you can still have a very solid line which isolates the wrong portion, because there are free, is redundant here, there are free possibilities. But again, this is an unknot, so it will be undone in no time, and it only works because there is tension on it. So I repeat the sequence for creating it. You might want to try to do it following any other website by having things going around, and it's almost impossible. I bet you on that. So you create a loop, small loop, large loop, in the same direction. You're always doing the same gesture to create the loops. So you store your energy here, and use the other thing as a stabilizer. It stabilizes this way, and it stabilizes this other way. And then you make it as large as needed. And by pulling, it will be the two loops here will be completely stabilized and will block the movement of the rope. And again, it's easy to undo. I want to talk a bit more about the bowline. The great point about the bowline, the reason why it is so popular, is that in spite of being slightly complicated to build, it has all these beautiful properties that it has, of being very stable, very good. It doesn't flow unless there is a huge pressure, but it is also very easy to undo, and in order to undo it, you have to do this operation. You have to break it here. So it's easy to undo, because the way it is constructed, in French it is called the chair's knot. So le nœud de chaise, because it looks like a chair, and you just open up the chair like this, and then it is a real knot. It's not an unknot, but it's easy to undo because of its geometric properties. Another knot which is done by operating directly on the standing end without consideration of the working end is the handcuffs knot, and I will need later on a demonstrator to show how it works. So it is again created by, looks like the ship shank, but it is one step less. So two loops, and then the loops enter each other in the only possible way, because any other way is going to make it impossible to stabilize the knot. And then if the gentleman could hand me his hands. Come closer. So this is a handcuff knot, which can be used for tying two objects together. So the name is a bit police-like, but the way it works is, and again, it is an unknot. So the prisoner who knows that it is an unknot will have a nice and easy job to untie it. I'll redemonstrate it. again, it's very difficult to do this knot by going around with a working end. You make a loop, and you make another loop. And then these two loops can only stabilize each other there is only one way. So if I enter this in the wrong way, it's not going to stabilize anything, it's just simply going away. So I have to use this portion to stabilize this loop, and then I have to let it enter like this, and this portion to stabilize the other loop, which is disappearing actually in the process, which is quite beautiful in a sense. There is a beauty to it. And so this is unstable in the sense that you pull and it goes. It's not a knot, it's a knot. But once you have an object, two objects actually into it, you can, it's very useful for carrying around a pole, not only for handcuffing. So if the gods of knotting help us, you might. Because you can open it up in different positions of the pole, and friction is going to hold it in place in a way this pole is not allowing. But one more time, once it is used, no problem. It's not enough. So one more thing I want to say, there are some knots which are totally forbidden in sailing. This is one. You never do this, never ever, because once you have it, you need devices to untie it, a marlin spike to enter it. You might want to have something here tight, which blocks, for instance, the flow of a rope. You want to avoid that certain rope just goes away, so there is a ring to keep it, and if it is open, then the rope is going to go away. In that case, you create a different knot, which is an 8-form knot, a figure of 8 knot, which is like that, it's an 8. Which has, again, geometrical properties like a bowline that you can easily untie by changing the shape of the knot itself, the overall shape, so the overall shadow, so to speak, of the knot, without acting on the pieces of rope. One of the points I want to make is that when you knot, as a knotter, it's not just the understanding of the geometry that matters, but of the physics, of the forces. But you feel these forces, because when you do this, you feel that there is a tension in the torsion. Or when you do this, well, you feel in your hands that things are dynamic, and not just you're not just drawing a shape in space. You're manipulating stuff, and the stuff has physical properties, and this feeling is part of the knotting knowledge. It's not a decoration, another decoration. So this is why I know that if I do a bowline like this, I have to enter in a certain way, because I feel the way it's going to untie if I leave the pressure here. Rings are unstable entities because they contain energy. So we want to get back to normal. So you have to, when you construct a knot, you have to keep rings in shape. Otherwise, the knot goes away. So hands are an important part of knotting, of course, and there is a feeling of the properties of a knot which is vehiculated by the hand. So at the beginning, of course, there is the half hitch. The half hitch is it's not clear what it is. I'm not sure it is a knot. It's a knot ingredient. It works like a knot in certain conditions. People talk about it as if it is a knot, but I don't know exactly. You have a half hitch. To see what a half hitch is, you have to make sure that you get the difference between just having something go around a pole, or something going around the pole and then pulling in the opposite direction. So at this point there is a tension here, a friction between the two parts, which is blocking the movement. But of course, you need a tension either way. So this is the half hitch. It is presented in textbooks as a knot. So let's say it is a knot, because there is a lexicon for that. And the clove hitch is actually simply the superposition of two half hitches. One is here, and the other one is here. So now that looks more like a knot, but it is actually created by the superposition of two half hitches. And this superposition is the same, as you can see by redoing this, that you obtain by creating two loops, 1 and 2, and stabilizing them with an external object. And one more time, this is not a knot, topologically speaking, because it just unties. One problem that I have theoretically is that is this object here part of the knot or not? This is the great theoretical point. If we want to model the knot, we are modeling a certain shape which is keeping the rope from flowing. So maybe this is part of the knot. In extreme conditions, this is part. The object the knot can be reflexive, so it can be part of it. If I can tie very simply a clove hitch on this piece of rope by creating my two half hitches. It's not a great knot. Nobody uses it for a number of reasons, but it's working.